Hello everyone, I'm Rishi Ranjan and today I'll be presenting the paper Symbolic Execution with SymCC. Don't interpret, compile. So this paper was presented in USENIX 2020, which is a top tier security conference, and the authors of this paper are Sebastian Poplo and Aurelian Francillon, who are from the Eurocom University. So first up, what I want to do is underline the key idea behind this paper, and then we'll go through and understand each and every aspect of it. So, to sum up the entire paper in one line, is the idea of this paper is that interpreting any executable at runtime is a slow process, whether it be dynamic instrumentation or whether it be from any internal representation. So, instead of interpreting at it runtime, if we compile the symbolic execution capabilities inside the binary itself at compile time, then we gain performance. We gain huge performance when we are executing this program. Now, you might wonder what exactly am I talking about? What is symbolic execution? What is this runtime cost? And what is the compile time benefits that I'm talking about? So, in order to start, let's begin with symbolic execution. So, to understand symbolic execution, let's consider a very simple program that will be our test case. In this program, we have a function called foo which takes three variables x, y, and z. All of these are user defined, that is, they are taken as input from the user. And there is a conditional on, there is a simple like function where each of these variables is compared to a value. Its range is checked within certain value. For example, you can see in the first if statement where x is checked to be within a huge number, which is 1 2 3 4 5. Then inside that if block, there is a check on y where its range is checked to be if it's between 434 and 9402 or not, and so on. So this is a really simple program which will be our example use case. Now, when we execute a program, what we'll do is we'll provide three concrete values to these variables x, y, and z. Now, these values can be anything. For example, I can put x to 32, y to 4324, and z to 123. It doesn't matter because the values itself are fixed, and these are fixed by the user when it provides it. Now, we can call these executions in which the value of every variable is fixed at runtime to be called as normal execution or concrete execution, and we'll look why these are called concrete in a minute or two. So with that definition out of the way, we look at the program from a different perspective. Let us try to convert the program into a branch tree where into a simple CFG, which is a control flow graph, where every conditional of the program is a node in the tree which has a false and a true branch coming out of it, or children coming out of it, depending on the whether the conditional is true or not. So for example, for the first conditional, if x less than 1 2 3 4 5, we have the first node which, if it is not true, leads to false, where there is the return 20 statement. If this conditional is true, we go into another conditional, which is where the range of y is checked, and then it again has two children nodes which go from false and true. Now if this conditional is true, we return 0, and if it is false, we go to another conditional, and so on and so forth. Now if you might have guessed that any value of x, if we consider the first conditional, which is a conditional on x, then any value of x which is less than 1 2 3 4 5 leads to the true branch of the program, right? So what we can do is that we know that the sample space of x is any integer value from negative infinity, let's say, to positive infinity. Of course, the value of int is fixed between two numbers, but it can be any value in this range. However, when we say that any value of x is less than 1 2 3 4 5, then it leads to the true branch of this program tree. Then we are essentially dividing the entire value or sample space of variable x into two compartments. One compartment is where x is greater than 1 2 3 4 5, and one is where x is less than 1, 2, 3, 4, 5. And any value in compartment A which is less than 1, 2, 3, 4, 5 will lead to the true branch, and any value in compartment B which is greater than 1, 2, 3, 4, 5 will lead to the false branch. So we can say that we have essentially divided the sample space of the variable x into two classes of it, into two simple classes, where no matter what value we choose from any of these class, the program execution has no effect on the value itself. So with this we kind of define a newer type of execution in which the value of x is not fixed, but it belongs to a specific class in its sample space. For example, it can belong to the class where x is less than 1, 2, 3, 4, 5, right? So this raises a question in front of us, that why not use class of inputs instead of concrete values, where we want to explore the program space deeper and deeper. Since executing for every input is a very tedious task because the sample space is so big for even one variable, so executing on a class of inputs which covers a lot of inputs in a sample space in one go is a very good option. Now, for example, let's look at this, that let's say the value of variable x is 1, 2, 3, 4, y is 4, 3, 2, 3, 4, and z is 4, 32. Now what symbolic execution does is it ditches all of these variable values, that is, it just crosses out, let's say, all these values for once, and instead it defines x as a variable symbolic value a1, y as a symbolic value a2, and z as a symbolic value a3. Now let's say that internally symbolic execution engine, or our symbolic executor, it applies these constraints on a1. For example, it says that whatever the value of a1 is, it belongs to a class which satisfies the constraint that it is less than 1, 2, 3, 4, 5. For example, a2 belongs to a class which satisfies the constraint that it is less than 434, and a3 belongs to a class which satisfies the constraint that it is less than 233. Now a1 can be any value in this class, but the program branch and the program path that it takes is fixed now for this class of inputs. So we have essentially covered all kinds of executions, all kinds of program path which could be taken by this combination of class of inputs. So symbolic execution has kind of helped us to cover a lot of the program space in one go. Now you may wonder, like, now that we know kind of what symbolic execution is, where we are not actually giving fixed values to the program, but symbolic values which are determined by a symbolic execution, but what is the actual use case of symbolic execution? So the major goal of symbolic execution is to explore all possible paths of a program using a class of inputs instead of an infinite sample space, as we saw, of concrete values. So now what this exploration helps is, it helps us in finding bugs in the program, and we'll see how this happens, and it also helps us in proving correctness of the program. Now let us look at it a bit about how symbolic execution engines are implemented actually, because these are really complex pieces of software. So understanding how they're implemented is an important aspect. And the essence of this paper is actually in the implementation part of symbolic execution engines. Like, it does not give us a newer symbolic execution technique, but it gives us a newer way to implement symbolic execution so that it is much better and much faster. So there are like multiple current approaches to building a symbolic executor. For example, three of the most famous ones are S2E, there is a executor called CLE, and there is an Anger named executor. And all of these are like open source, so you can play around with it. Now they also have like runtime interpreters which are used to collect and solve constraints. Now I've shown the flow of symbolic execution in this flowchart. So what happens is that we have a target program which has to be run under a symbolic executor. Now the job of the symbolic executor is to find new paths within a program, right? So now what it does is it extracts the control flow constraints from the program, this symbolic executor. For example, the constraint in the previous program was x is less than 1, 2, 3, 4, 5, or y is less than some value, or y is equal to some value, and these are the constraints that it extracts from the program. Now once it has the constraints of the program, it knows that if I satisfy a constraint, I'll get to a new path, or if one constraint is being satisfied, then if I produce inputs which do not satisfy this constraint, we'll get to a new path. And this is the logic that a symbolic executor follows. So it collects all these constraints and gives it to a symbolic executor runtime, which is nothing but an SMT solver. Now these solvers are meant to solve such equations or such constraints and give us value for all the variables which satisfy these constraints or not unsatisfy these constraints. So these runtime solvers, they generate new inputs which cover new paths in our program, and that is the job of the symbolic execution runtime. So we'll focus on this entire process in two halves. In first half, we'll focus on how a test program is run under symbolic executor, and then we'll focus on how symbolic execution runtime solves these constraints that are extracted from the program. And QSIM has different solutions for both of these aspects of symbolic execution. So now let's get to the first part, which is that running the program under test under a symbolic executor. So the traditional or the standard way of doing symbolic execution is that we have a target program, which is a bit code or a machine code, whatever. Then we interpret this program at runtime, and when we interpret this program, we insert newer instructions inside the program in each execution, which extract the constraints from the program and which give the constraints to a solver to solve it. For example, I have a very simple example here where there is a function called isDouble. This is just LLVMIR. So now that we have an isDouble function which takes two arguments, so what we do is that we have a simple loop in the interpreter which gets the instruction, which kind of determines what kind of instruction we are trying to execute. Then we get the operands of these instructions, as you can see, where it is auto result is equal to instruction dot operand 0 left shifted by instruction dot operand 1. Now obviously this depends on what kind of instructions we have, and then we try to generate the expression out of these operands. And once we have the expression out of these operands, then we try to solve this expression and set the value to our generated new input. So to simplify this technique, there are two main ways in which this runtime interpretation is done. The first technique is in which we have the machine code, that is the x86, ARM, all of these assembly code for the program. We convert this code into IR code, which is the internal representation, kind of a simplified assembly, you can say. So we convert this machine code into a simplified assembly at runtime, and then we interpret this simplified assembly or instrument this simplified assembly code at runtime, which is run by our interpreter. Now this above technique or this above flow is followed by CLI as to these symbolic executors. Or there is another technique in which we directly take the machine code and we instrument this machine code directly at runtime. So of course it requires you to write instrumentation code, which is also assembly. Now obviously the major difference between these two is that the first approach is much easier to implement because generally the IR code, the internal representation code, is much simpler. It has much fewer instructions, so you have to deal with a lot fewer instructions than in machine code. So the second approach is much more difficult, the first is easier. However, the IR code is much less optimized than the machine code, and when you're working with machine code, you can optimize your symbolic execution code as much as you want. So the second approach, even though it's difficult to implement, is much faster than the first approach. Now the first approach, as I told, is the one that is followed by CLI, Anger, S2E, while the second approach is followed by one of the most famous symbolic executors, which is QSIM. Now, as you might have noticed that both of these things, even though the second one is faster, both of these approaches are done at runtime. That is, every time the program is re-executed, all of this process has to be done. All the instructions have to be instrumented, the constraints have to be extracted, and that's how the process works. So, the first novel idea or first major idea of the SymCC paper, SymCC tool, is that instead of doing all of these runtime instrumentations and runtime symbolic execution capabilities, why don't we do this at compile time? Because as we all know, like, that doing things at compile time is much faster than doing it at runtime. So that's the approach that SymCC takes. So if we have the program code, that is the actual source code of the program, and we have its IR representation. IR is like a compiler level language that any compiler uses to, like, get you machine code. So if we have the IR level representation of the program, then SymCC is basically a compiler which puts in the entire symbolic execution mechanism inside your binary at compile time itself. So once you do it at compile time, so the binary itself has all the abilities to symbolically execute itself and generate new program paths using it. So this leads to much faster symbolic execution, as we'll see, and we'll get to it later. So yeah, so that is the first major improvement that SymCC proposes over existing techniques, because none of them use compile time instrumentation. The next the next novel idea that SymCC proposes is the support for any runtime for symbolic execution. For example, there are very good symbolic execution runtimes, like there is a QSIM runtime, which, what I mean by runtime is that runtime basically focuses on the second part of symbolic execution, which is the constraint extraction and constraint solving during the from the binary. So what SymCC does is it allows us to use QSIM symbolic runtime. So QSIM execution runtime, that is QSIM's constraint solving, QSIM's constraint generation, these have very good ideas. For example, QSIM does not overcomplicates its constraint. That is, a program may have a lot of constraints where only a few of them might be related to actual program inputs. So QSIM just takes those constraints which are related to program inputs, and it calls it controlled constraint generation and so on. So SymCC has an option to use such a powerful symbolic execution runtime too. It also provides its own simple runtime backend which can be used. It is a really simple SMT solver based on the famous Z3 SMT solver. Now, in order to evaluate the work that SymCC does, we first have to understand that what exactly are the parameters that SymCC should be able to elevate, or what are the things that SymCC should be able to improve. So there are two major things that SymCC should improve. First up, the execution speed. Now, whatever the overhead of symbolic execution is, SymCC should be able to better this and perform fast execution of the program even when it is symbolically executed. Now the second thing is program coverage. What this means is that if you have a symbolic executor, you should be able to cover more and more of the program, and thus any symbolic execution, including SymCC, should be able to cover maximum of the program paths. So let us first focus on the execution speed, or evaluating execution speed. So there are two kinds of experiments that are mentioned in the paper to judge the execution speed of SymCC. So the first one is when the program under test, or the PUT, is performing purely concrete execution. What this means is that there are no symbolic inputs to the program. So we want to see that how much overhead does the compile time symbolic execution add compared to runtime symbolic execution? That is, when we are doing concrete execution, it should be as close to the native execution speed as it can get. And you can see that there were around 40 programs which were tested, which were taken as the test bench, and the range of run times for SymCC is very close to the native execution speed. And the next experiment was when there is execution with purely symbolic inputs. There we can see that the average time of SymCC is just above 1.5 seconds, while for QSIM this goes to around 10 or 11 or 12 seconds, while CLI is also on a similar level. So SymCC is on an average 10 to 12 times faster than QSIM and CLI. So there is a huge performance improvement that we get by doing things at compile time or by doing things in SymCC style. Now the next thing is that program coverage. How much more paths does SymCC cover? So in order to read these graphs, I'll give you a simple metric that if a square on the graph is blue, that means that the bluer a square is, the more path SymCC covered for that program. And if it is red, that means that CLI or QSIM covered more paths in the program. So for example, the first graph is for CLI and SymCC, and as you can see, most of the graph is blue, which means that for most of the programs, SymCC covered more program paths as compared to CLI. White means that both of them on an average covered the same amount of paths. While for the next graph, we can see between QSIM and SymCC, SymCC still dominates, although the domination is much less as compared to QSIM, but it still tends to dominate and cover more path on majority of the programs under test. So SymCC also excels in getting better program coverage. Now you might be wondering that, yeah, sure, that symbolic execution gives us this great coverage and get better execution speed with SymCC, but what am I supposed to do with this? What is this information useful for? So the most important thing in this presentation is giving you an idea of how symbolic execution is used. So I'll give you two major use cases of symbolic execution. The first one is hybrid fuzzing. So symbolic execution has a very good ability to explore deeper and deeper paths in programs and solve really difficult constraints which are very difficult for fuzzing to solve. And once it does that, it can help fuzzing to find deeper bugs in the program where fuzzing might be restricted due to difficult constraints like inequality check constraints and things like that. Now another important use case of symbolic execution is to prove program correctness. Now symbolic execution is a possible substitute for model checking and other theorem proving techniques which are currently used to prove the correctness of a program, and symbolic execution can be used to make it much easier and prove that a program is correct over all class of inputs, as we saw. So these are the major use cases of symbolic execution currently, and to explore symbolic execution currently, I would greatly recommend looking at SymCC source code, how they implement a compile time instrumentation engine, how they do their runtime. I would also recommend reading a bit about the first symbolic execution engine, which was built in some 1971, which basically was the basis for all of this. So there's a lot of material and stuff to go along with symbolic execution. Yeah. Thank you. So that was my presentation. Thank you.